Good morning and welcome back to CS 2100. So as we start, I want to know if anyone had any questions. Okay, so I think if you've all looked at your announcements in Canvas or looked at your email, you've discovered that the grades on quiz 3 are out. So look in Canvas and look in Gradescope if you have any questions about your grading. Let's see, the median grade on this quiz was 85. And the mean was 82 point something or another. So the grades were skewed towards the higher end of that. And I guess I'm happy about that, or else it was too easy. That's a joke. Don't get upset. So I just want to remind you that homework 4 is due a week from tomorrow. So you actually can take a deep breath, get it done, take the time. And quiz 4 is 2 weeks from today, Thursday, March 25th. My dates may be off, but at any rate, that's close. Thursday, whatever day that is. So don't be surprised by it. Okay. Are there any questions before we start jumping into chapter 4 on functions and relations?
Could you repeat that last thing you said right before you said quiz 4 was 2 weeks away? I didn't catch that last part.
Just that it's Thursday, March 25th.
Oh, okay.
Okay, that's on your that's in the modules, it's in the syllabus, it's everywhere you can think of. So I'm just reminding you all that there will be a quiz 4 on March 25th on the material in chapter 4 that we cover, the sections that we cover. So with that.
I had one more question about the quiz also.
Yeah.
There's a Piazza post about question 4 on the quiz. Was there was that question like correctly written? Like, was there a valid answer for that question?
Yes, there was a valid answer. The question about the issue with the question 4, I don't know what the question was per se, but there were multiple solutions to that question, and some students had a somewhat different one that was correct, but not graded that way. So the TAs went back and it's been regraded.
Okay.
Okay. So if you still have questions about your grade on it, you can send a note if you want it regraded, or if you have a question about a solution, go to office hours or discussions and ask. Okay? That's the easiest thing you can do. Any other questions? Okay, in that case, let's jump in. I already did that. So last time we were talking about relations, and we defined functions and we defined relations. And we started talking about relation composition and function composition. I want to go through that again. So let's talk about relation composition again. So if R1 is a relation with domain A and codomain B, remember a relation is basically a set of ordered pair on the cross product of two sets. And it can be defined in any number of ways. That's all it needs. The first element of the pair is called, or the set of elements from which the first elements are taken is called the domain. The second element is called the codomain. Let R be a relation with domain B and codomain C, R2. Then the relation R3 is defined as the set of all A comma C, where A is in A and C is in C, if there exists a B in B such that AB is in R1 and BC is in R2, and it's called the composition of R2 with R1. Notice how it's written. Okay, the one you apply first is on the right, just the way it is with functions. The one you apply second is on the left. Okay, so in this case, what is R1? So we have a set of ordered pairs. So we say R1 is equal to the set. And what is it going to be? We have to list all the ordered pairs here because it's just finite. So is one part of any pair?
No.
Right, it is not. So 1 doesn't appear as the first element of any pair. What about 2?
Yes,
What does 2 go to?
2A and 2B.
So 2 goes to A and 2 goes to B. So 2 is the first element in 2 different
Hold on,
ways.
it's 2D, not 2B.
Oops, you're right. It doesn't go to B, it goes to D. Thank you. To D. Thank you very much. Okay, what does 3 go to?
3C and 3E.
3C, it's a comma, and 3E. And where does 4 go?
4E.
Does 4 go somewhere?
Yeah, it goes to E. 4
Good,
goes
4 goes to E. Okay, tell me what R2 is. So R2, we look at things and say, does A go anywhere?
No.
Nope. So there's no pair here with A as the first element. What about B?
B goes to Q.
B goes to Q. Only 1. Where does C go?
C goes to S.
Very good. C goes to S. And where does D go?
D goes to R.
D goes to R. And E?
E goes to Q. E goes to P.
P. Good. Is R2 a function? Remember, functions are subsets of relations. Is R2 a function?
Yes.
Is it?
Nothing
Why?
is a function.
I would say no.
And why? Who is that? And why would you say no?
Isaac Christensen says no because A doesn't have anywhere to go. It's
That's
not mapped to
exactly
anything.
right. Very good. Okay. You look at it and you say, well, gee, that could be a function because B only goes to one element and C only goes to one element and D only goes to one element and E only goes to one element, but A doesn't go anywhere. So it's not a function. Every element in the domain has to get used for it to be a function, but not for it to be a relation. Okay. All right. Okay. So now we got the hard one. What is R3? So we trade, whoops. How do we do this? Well, what we do is we trace. We know 1 doesn't go anywhere, so it isn't part of any pair in R2 of R1. So let's ask the question, what about 2?
2 goes to D and D goes to R. So
Yes,
2 goes
so
to R.
goes to R. We say that because, see, we have D in there. And so 2R is an element of the composition because there exists an element in B, namely D, which 2 comma D is a pair in R1 and D comma R is a pair in R2. Okay? Good. And 2 goes to A, but A doesn't go anywhere. So that's it. We just have 1. Now, what about 3?
3 goes to S and 3 goes to P.
3 goes to E and E goes to P.
Yeah.
3 goes to P. Anything else?
3 goes to C and C goes to S. 3 goes to S.
Right, so 3 goes to S. Very good. All right, what about 4?
4 goes to E, E goes to P, so 4 goes to P.
Very good. That's it. Does everybody follow that? Are there any questions? It's function composition, I'm sorry, relation composition. Okay, that's our solution. Now, function composition, it works kind of the same way. Christopher, you had a question.
Yeah, just a quick question about the notation. So do we need those arrow diagrams, or I'm sorry, not the arrow diagrams, but the domain pointing to another domain in our definition of R1, R2, R3, or is that just for functions?
Now that's a good question. Okay. So what we tend to say when I wrote it out here, but you could say R1 is, I'm sorry, you say R1 is a subset of A cross B defined as, and then you do the picture or you give the pairs. Okay.
And can I follow
And
up?
then R2 would be a subset of B cross C, and R3 would be a subset of A cross C. Okay?
Could I just ask another question about that? So in the text, they have a notation that's something like R colon and then A with an arrow pointing to B. Is that the same as what you said here? R1 is a subset of A?
That's also using, that says domain and codomain. So that's kind of the function notation that we use.
Okay.
So
Okay.
you can do that, or you can use the cross product. They're all correct. Okay. If you're looking at something new and you're not sure, don't make up your own. Okay. Use one of the ones you see either in class, in discussion, in office hours, or in the book. Okay.
Okay. Thank you.
Okay. Good. Okay, here we are. Function composition. Now, function composition, we say F maps A into B and G maps B into C. Then we define H as the composition of G with F as H. And then what we do is we say, look, see, we apply F to elements of A, and then we apply G to the result of that. And we write it the same way we wrote the relations, G circle F. So when you say circle, it sounds like G is first, but it isn't. It's really, you're saying G of F. Okay? And if you say it right, then you'll remember what the correct order is. This could be confusing, so try to be careful. Don't let it get you confused, all right? And the composition starts out, H goes from A to C. And the picture there sort of says it, okay? Remember, as a function, every element of A gets mapped to something in C. And you knew that every element of B got mapped to something in C, but you don't necessarily use every element in B. It depends what A is mapped onto. So all of A could be mapped onto one element of B. And so when you then compose G with it, you map all of A onto one element of C. Okay? Good. Okay, so let's look at an example of function composition. Two examples, actually. So suppose we look at F going from the integers to the integers, and it's the mapping 2 times m plus 3, where m is any integer. And then we have G going from Z to Z by G of n is equal to n squared. Okay? So if we apply F and then G, Dane, you have a question?
Yeah, sorry to interrupt. Shouldn't in G compose f of p, shouldn't it be 2p plus 3 squared? since the argument is P, not M.
Oh, gosh. That's what happens when I just copy stuff. You're right.
Okay, thank you.
Thank you. I think I got the second one right, but not the first one. Thank you very much.
You did, and it should be 2q squared plus 3.
Oh, gosh. Thank you, guys. If I didn't make mistakes, how would I know you're listening? Thank you. Okay, then g of f of p, we apply f first and get 2 times p plus 3, and then we apply g to that, and we get squared. But if we apply g to q, we square it, and then we apply m to it, so we go 2 times the result of g plus 3. So even when the domains and codomains are the same for both, and you can talk about f of g and g of f, composition is not commutative. You see, we get totally different answers when we compose them. So if you compose in the wrong order, it's likely you'll have the wrong answer. All right. Onward. Let's do a practice problem. Okay. Practice problem 1. Here we go. We're going to do something on the set X. We've done stuff on a simple set before, and we're going to go with that. We have the set ABC, and we're going to look at the one set diagram for ABC, for the function which maps the power set of X to the power set of X, with the rule that C of A is equal to X, the whole set, minus A. Namely, we map a set to its complement in X. Okay? So now we're asking, what is C composed with C? So let's start out the simple case. Let's look at the empty set. And that's wrong. That's the empty set. Let's look at the empty set. Where does it map to under C? Well, it's X minus the empty set is still X. So that maps to X. And then we apply it again. What does X map to under C? Well, its complement, X minus X, is the empty set. So that maps to the empty set. So this is the mapping T. Okay. So now let's look at T of A. A maps to its complement. So it maps to BC. And then we apply it again. And where does BC map to? It maps to A. B, where does B map to under C? You've seen this diagram before. B maps to AC, its complement in X. And then AC maps to B, its complement in X. Where does C map to? Well, C maps to AB, its complement in X, and AB maps to its complement in XC. Okay, let's do 2-point sets. AB, where does it map to?
AB.
Yeah, AB maps to C, and C maps to AB. AC, where does that map to? Well, under C, the function, it maps to B. And then where does B map to under the function C? It maps to AC. Okay. ABC. Oops, I forgot BC. Got to do BC first. BC maps to A under C, and then that maps to its complement, namely BC. And finally, we have X, that's ABC. X minus X is the empty set, and then the empty set map back to X. So under the mapping C composed with C, we just get the original values back again. Lewis, what is your question?
I had a question. So if we were given this problem on a homework or a quiz and we weren't giving that diagram, do you expect us to draw that diagram on the left, or will that be given to us?
I would, it depends on what the problem is, what you have to do. You could be asked to draw the diagram of the composition. What would the composition diagram look like? If I had the empty set, AB, AC.
It would be little circle arrows, right?
Yes. Let me draw it for you. BC. It's very good. A, B, C. And what do we have over here? We have C, B, A. So what we'd have is something that looks like this. You can draw your circle, your loops the other way around, your arrows. You know, it's up to you. Does that make sense? Everything is mapped to itself under the composition of C with itself. Which leads us into, we have another one problem. Let me talk about the identity first, and then we'll go back to another composition problem. So for a function, if A is both the domain and the codomain, then we can define a mapping I of A such that I of A is equal to A. Okay, and that's exactly the mapping we just had, where your one set diagram would be little loops from A, each element to itself, and nothing gets mapped to anything different. And everything has a mapping. It's one-to-one and it's onto it. It's always that, and it's called the identity function. Okay, so we can use the identity when we're talking about inverses. If you have two functions, A from F from A to B and B from and G from B to A, they don't have to be the same, A, capital A and B. They're inverses of each other if G composed with F is the identity on A and F composed with G is the identity on B. Okay, this is sometimes much easier to prove than using the definition of inverses. That sort of is a little convoluted, but this is much easier to prove. The identity relation on A cross A, there is something called the identity relation, and that's just the set of ordered pairs A comma A. Okay, now let's go back to practice problem 2. You're supposed to prove that the composition of relations satisfies the associative law. Okay, so there are relations. We know that relations are not commutative. We just did an example of that. If you compose them, it's not commutative. But here's the question, is it associative? Well, we're going to prove it. So we let A, B, C, and D be sets. Do you guys want to work on this one first? Good, work on it and then we'll do it. Okay, let's give it a whirl. So what do we know about this? Well, we know that T mapped with S, T of S, all of R, is a subset of A cross D. And T of S of R is also a subset of A cross D. Okay, so we say let little a d. What are we going to prove, by the way? We have two things we have to prove. We have to prove if something is in that subset, then it's in that subset. And then we have to prove that if something is here, it's in here, so they're equal. Louis, you have a question?
Yeah, so how did you come to the conclusion that it was a subset of A cross D? Is that just an identity we need to know? How did you determine that?
Well, because what do we know? We know that R is a subset of A cross B. And S is a subset of B cross C. And T is a subset of C cross D. Okay. And so we're going to look at this pair. And so what we have is, in order for there to have any elements, we have to know what the domain and codomain of the relation are. So we would take an element in A, and that's paired with an element of B, and then B is paired with C, and then C is paired with D. So that means that A and D, if you find B's and C's that satisfy these things in some ordering, which we'll get to, then you've got to have the first element has to be in A and the second element has to be in D. So let's look at what we have here. We have AD is an element of T of S of R. Okay. Now, by the composition, what do we know? We know that that can be an element of this side by definition. There exists, so R goes from A to B, and T of S goes from B to D. That's the composition rule. So what do we know? We know that in order for that to be true, there has to be an element in B such that AB is in R and BD is in T of S. That's the definition of composition, right? So then we go on and say, oh, now for BD, an element of T circle S, then there exists C in C such that B circle C is in capital S and C circle D is in T. I mean, C comma D is in T. Those are definitions of composition. All right. So now we have a bunch of stuff going on. Okay. So now we look and we say, does, I wish I could write. does A is, or should I say is A circle C in S of R? Well, yes. Yes, since A circle B is in R, and not circle, A at comma B, and B comma C is in S. And then we say, is C circle D in T, and yes, since we have that. So AD is an element of T of S of R. Okay? So what you're doing is slowly peeling it apart by the definitions of composition. Each time you're applying, composition is defined as a binary thing between two sets, two relations. So you're taking it apart in pairs. Okay? Now, doing it in the other direction is exactly the same. It's basically starting out saying if AD is in T of S of R, then, and you go the other way around. So in that one, you're going sort of upwards. Okay, let's move on. Any questions about how to do this kind of thing? Good. Okay, we talked about the identity. Let's do practice problem 3. By definition, we know if there's an identity, then F from A to B and G from B to A are inverses of each other if and only if G of F equals identity on A and F of G is the identity on B. That's true for functions. Now let's ask the question, if R1 is a relation on the pair XY, the binary relation XY, and R2 is a relation on YX, is it true? That's the question. Is it true that R1 and R2 are inverses of each other as relations if R2 of R1 is the identity and R1 of R2 is the identity on Y? Well, let's look at an example. So remember what an inverse of a relation is. We just reverse all the order of the pairs. Okay, that's the definition of an inverse of a relation. Okay, so if R1 is a relation on XY, R2 is a relation on YX, and we define it as the inverse relation, then let X equal this set 1, 2, 3, 4, and Y is X. So we're going to make life easy. It's the same set. And we let R1 be the pairs 1, 1, 2, 2, 2, 3, 3, 2, and 4, 2. Okay. Then R inverse, R1 inverse, is equal to, well, gee, that's the first element, that's the second in the inverse, the first and the second in the inverse, 2, 2. But now 2, 3 goes to 3, 2, and 3, 2 goes to 2, 3, and 4, 2 goes to 2, 4. So we know what the inverse is. So let's look at R inverse, R1 inverse of R1. Okay. What do we get? Well, we apply 1 goes to 1 goes to 1. That's pretty straightforward. 2 goes to 2 goes to 2. That's straightforward. 2 goes to 3 and 3 goes to 2. Well, we already have that one. What else do we have? 3 goes to 2 and 2 goes to 2. So we already have, where's that? Somewhere we have 3, 2. Ooh, I left one out. Let's go back. We already have 3, 2, but 3 goes to 2 and 2 goes to 3. So we add 3, 3 is now something there. We had 2 goes to 2 here and 2 goes to 4 in the inverse. So we have 2 goes to 4. That's a new one. 3 goes to 3 is a new one. 3 goes to 4. Let's see. Let's see what we have. We have 3 goes to 2, 2 goes to 4. So 3 goes to 4. 4 goes to 2, 2 goes to 4. So we have 4, 4. 4 goes to 2, 2 goes to 2. So we have 4, 2. 4 goes to 2 and 2 goes to 3 in the inverse. So we have 4, 3. So that's not the set of pairs 1, 1, 2, 2, 3, 3, and 4, 4. That would be the identity relation. So that's definitely not the identity relation. If we do R1 first, R1 inverse first, and then R, we get a different set. Again, it's not commutative, but we get a totally different set. And it is, again, not the inverse. I mean, not the identity. Okay. So we have that when functions are invertible as functions, then I apply the function and then its inverse, I get the identity. If I apply the inverse first and then the function, I get the identity in the code domain. Okay. All right. So let's talk about types of functions. Oops, let's take our break. You can ask me any questions you want while we're on break.
Could you help me understand even better the identity relation and what does it mean?
I'm sorry, say that again.
The identity relation. Does that just mean like the same thing as in both sets?
The identity relation, if I call it that, the identity relation on a set X, for example, this set X, would be equal to the relation A goes to A and only A, B goes to B and only B, C goes to C and only C, D goes to D and only D. Do I have everybody? Oops, that's the last set. Okay, so the identity relation is actually a function. Every element goes to something and it goes to itself. Okay.
Okay, and there's no like pollination or anything. There's no A, B, C, D, C, B or nothing.
If it's identity, it's identity. That says every element goes to itself.
Okay, cool.
Cool, yeah. Okay, I'm going to erase this because we're on a different topic now. I don't want to get confused later. Okay, are we done? Are we up yet? I guess one more minute.
I have a question then. So with what we just proved, that means that if we want to, if we want to use that relation, or not that relation, that that proof where two functions times e, to prove an inverse, basically, we have to prove that they're both functions first, right? In order to use that. Okay.
Yes. They have to both be. We're going to have a theorem about that in a few minutes, actually. That makes life much easier about proving inverses.
All right. Thank you.
Okay. So remember what it says here about inverses is that they both have to be functions. And what do you know about functions? For f inverse to be a function, then f had to be, well, I'm going to define that right now, actually, right here. Okay, it's time. A function is called onto or surjective. I don't know if our book uses that word. If every element in the codomain of, sorry, I have problems typing, of the out is, it's not every element in the codomain is the output of some element in the domain. If, yeah, is the output of some, so that is if you have a map F from A to B, it's called onto if and only if we take an arbitrary element in the codomain and we can show that there's at least one element in the domain that maps onto it. Okay? A function is one-to-one if there are no elements in the codomain that is the output of two different elements in the domain. So what does that say? That says F from A to B is called one-to-one or injective if for all x and y in A, f of x equal to f of y implies that x equals y. Okay. Now, what does that mean? It doesn't have to be onto the codomain. Okay. But what it means is every element in the domain has exactly one arrow emanating from it. Okay. And so it says there's one arrow emanating and every element has one. Okay. Not two, not zero, but one. Okay. It does not mean it maps onto the codomain. Okay. A function is called in one-to-one correspondence or bijective. It's if it's both one-to-one and onto. Okay. So that means if you're going to try and prove something is in one-to-one correspondence, or if it's bijective, you have to prove both that it's one-to-one and that it's onto. Now, proofs, when you're trying to say, I want to prove that I have a map that's onto, you always start out by saying, let B be at B. Give me an element, an arbitrary element in the codomain, and I'm going to find an element in the domain that maps onto it. Okay? Every proof regarding proving onto says that. If you're proving one-to-one, you always start out picking two elements in the domain. Notice they start out picking in two different places. You pick two elements in the domain and say, suppose that they have the same image. They map to the same point in the codomain, and then prove that means they have to be equal to each other. Okay? All these proofs start out the same way. That's the formula. We don't give you a formula for the rest of the proof, but you always know how to start it. So let's do a problem. Practice problem. Okay, so we're going to let A be the set of all real numbers that are bigger than 1. Bigger than or equal to 1. And we're going to let F be the mapping from A to A in the form f of x is equal to x plus 1, and ask, is F onto? Now, if I want to prove it's onto, if I think it is onto, what do? I start out and I say, give me some y, and let me show it's equal to 1 over x plus 1. Okay, so Okay, so, but should I pick an arbitrary element? I kind of can. So what would I do? I would say, suppose, yeah, suppose y is an A and y is equal to 1 over x plus 1 for some x. What does x have to equal? Well, in that case, then x plus 1 would equal 1 over y, and x would equal 1 over y minus 1, if it were true. Okay, so that looks really great. I found an inverse function. Not quite. When is this not a function on the domain A?
Y equals 0.
Well, that would be a problem. But y equal to 0 that's not in the domain. What other case would that be a problem?
Maybe y equals 1.
Very good. Exactly. If y equals 1, then x would equal 0. But remember, this function only maps elements from A. So x is not an element of A, and f is not onto.
Sorry, I think you should write y equal
I'm sorry?
y. I think you should write y equal 1, not y equal 0.
No, then x would equal 0. If y equals 1, then I have x is equal to 1 over 1 minus 1, which is 0.
Yeah,
And
so
that would say that under f of 0 would equal 1.
Now, what you wrote
only
was y equals 0.
I'm sorry?
What you wrote is y equals 0. You said y equals 1, but I think you had that in mind. So you say if y equals 0.
yeah.
Ah, thank you.
Okay.
Yes, he suggested y equal 1, and that's what I meant. Thank you. So remember, 1 is in the domain A, and f is supposed to map A to A. So since A is also the codomain, onto means that something has to map onto 1. But there is nothing that maps onto 1 that's in that domain. So it is crucial, the definition of domain and codomain are crucial to the answer to this. So let's look at this mapping Q. Whoops. So here, what we're looking at is G maps from all rationals to the rationals greater than or equal to 0. Okay? And we're defining it, G of x is equal to the absolute value of 3x minus 1. And ask, is G 1 to 1? I'm setting myself up to too many things here. Well, if I plug in, I say G of 0 is equal to the absolute value of 3 times 0 plus 1, which is 1. 1. Okay. Now it turns out G of minus 2/3 is equal to absolute value of 3 times minus 2/3 plus 1, which is equal to absolute value of minus 2 plus 1, which is equal to absolute value of minus 1, which is 1. Now, 0 is a rational number. No, is in Q, and minus 2/3 is in Q. And so we have two distinct values mapping onto the same value. Now you can say, well, how did you know to do that? Okay, reasonable question. Well, what I do is I say, let me look at the map of 3x plus 1 absolute value. Okay, and what you get, what does that look like? Well, 3x plus 1, when x is 0, y is 1, so it looks like this, kind of, and then it goes back like that. Okay, so what we're doing is saying, well, where does that happen? I could have picked anything else. All of these guys work, but I picked the easiest one. Or I could have picked, any of them. Okay? Okay, so here's the easiest way. A function is called invertible if there exists an inverse function. Okay, so if there exists a function f inverse such that f of x equals y, if and only if f of that same y is equal to x. So the inverse of the original function is the original function. So we have this. If I find the inverse of the inverse, that's the original. And here's the key thing. A function has an inverse if and only if it has a one-to-one correspondence, and that means it's both one-to-one and onto. Okay, both one-to-one and onto. It can be finite sets, it can be infinite sets. Okay, so you don't have to find the inverse. You know it's invertible if it's both one-to-one and onto. Okay, so one-to-one and onto is really important. Shall I say that again? It's really important, separately and together, because they prove invertibility. Okay, here's a practice problem. Going to let f be on the positive reals, and it goes from positive reals to positive reals. And we're going to define it as f of x is equal to 1 over x minus 1. Okay. That can't be. Yes, it can. No, it can't. That's a bad problem. I'm going to come back to that. Yeah, that's a bad problem. Okay, I'll come back to that. We'll do a different one. If f goes from a to b is 1-to-1, and g goes from b to c is 1-to-1, this is a proposition, then h, which is g of f, going from a to c, is 1-to-1. Now that's a proposition, which means you can prove it. Okay, and you should prove it. If f goes from a to b and it's onto, and g goes from b to c is onto, then h, which is the composition of g with f, goes from a to c and it's onto. And you should be able to prove that too. In fact, not only should you be able to prove it, but I think that's homework problem 6. So that's a good thing to prove, be able to prove. Remember, when you're proving onto, in this case, I'll give you the first line. We're going to prove h is onto. So what do we say? Let little c be in capital C. We start out in C, and then we have to prove that there's an element of A that maps onto it. Okay? Good. What about the first line here? Well, the first line here says, let x and y B, and A such that H of X is equal to H of Y. I gave you the first line of that one too. Okay? That's for you guys to work on at home. Okay, set cardinality. The word cardinality means the number of elements. And if you ask me where that came from, the answer is I don't know. It just is. So if we let f from A to B be a function where A and B are finite sets, and the number of elements in A is m and the number of elements in B is n, if f is 1 to 1, then m is less than or equal to n. Why? Because the image of f, okay, how many elements would be in the image if it's 1 to 1? Well, the same number of elements that are in A, which would be m. And you know the image is a subset of the codomain. So that says m is less than or equal to n. If f is onto, then m is greater than or equal to n. Why is that? Well, if it's onto, you know that every element in B has at least one element in A mapping onto it. So there have to be more or the same number of elements in A. Finally, if F is in 1-to-1 correspondence, what does that mean? It means it's 1 to 1, so M is less than or equal to N, and it's onto, which means M is greater than or equal to N. So that means that M has to equal N. Now, this is critical that they both be finite. So when we talk about infinite, the number of things in an infinite set, there's the notion of degrees of infinity. Okay, they're not all the same. So we call a set infinite if there exists a function f from A to itself that is 1-to-1 but not onto. Remember, for a finite set to itself that's 1-to-1, that means it has to be onto, because if it's 1-to-1, then its image has the same number of elements as it does, and it's a 1-to-1 correspondence. So this says 1-to-1 but not onto. An infinite set is called countable if it has the same cardinality as the natural numbers. It's called uncountable if it's not countable. Okay. Two arbitrary sets A and B, maybe they're finite, maybe they're infinite, we don't know, have the same cardinality if there exists an invertible function from A to B. Okay, an invertible function from A to B. So we know for finite sets, we know we have that nice little theorem above. For infinite sets, we have the fact that the definition of 1-to-1 and onto holds. Okay. So remember, the invertible function did not depend on finite or infinite. So the definition of invertible is that there's an inverse, and we have that if there's a surjection and a bijection, it's a 1-to-1 correspondence, and that means invertible by definition. Now, sometimes in order to prove invertibility, you don't necessarily want to start proving 1-to-1 and onto. And then there's the Cantor-Bernstein theorem that says if you have sets A and B, if there's a 1-to-1 function from A to B and a 1-to-1 function from B to A, then the sets A and B have the same cardinality. Remember, we didn't just prove onto. We said 1-to-1 in both directions. They can be the inverses of each other, but not necessarily. Okay, that's a biggie. So let's consider practice problem 6. And This is something close to what we've had before, but not the same. Let A be the set of all 3 element subsets of C, and B be the collection of all 2 and 3 elements subsets of 1, 2, 3, 4. Define the mapping from A to B of S as S minus the set with 1 element 5 for all S and A, and prove that F is onto. And then I ask, is F 1 to 1? Do you want to try this one yourself? The key things I would try is I would say, what is the set A? How many elements are in it? What does the set B look like? Okay. And then I'd work on proving it was onto. Okay. So why don't you give it a try? I'll give you a couple of minutes to at least start it, and then we'll jump in. Okay, let's jump in. What does the set A look like? Well, A is the set of all 3 element subsets of C. So let's work our way through here. We have 1, 2, 3. 1, 2, 4. 1, 2, 5. 1, 3, 4. 1, 3, 5. 1, 4, 5. 2, 3, 4. 2, 3, 5. 2, 4, 5. 3, 4, 5. Have I got that right so far? Yeah. Okay. Those are the 3 element subsets. Now, what is B? All the 2 and 3 element subsets of 1, 2, 3, 4. So let's do the 2 element subsets first. We have 1, 2, 1, 3, 1, 4. Right? And then we have 2, 3, 2, 4. And then we have 3, 4. Okay. Now we want the 3 element subsets. So we have 1, 2, 3. 1, 2, 4. 1, 3, 4. 2, 3, 4. Am I missing anything? I don't think so. I think that's it. We good? Okay. So the first thing to observe before we start in the depth of the proof is that if I look in A and I see any of the 3 element subsets that do not have 5 in it, how many of them are there? I'm hoping there are 4. If they don't have 5 in it, then when I look at taking them, everything in them that does not include the element 5, well, 5 isn't there. So it's the identity on those things. So what we have is that f of, let me write it like that, A, it's the set of sets. What is it? Well, these 3 element subsets go through unchanged. As long as they don't have a 5 in them, they aren't touched. So we have those. Okay, now, what happens to those 6 subsets that have a 5 in them? Well, the 5 disappears, and we end up with 2 element subsets. So we have 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. Okay, so now we know what the mapping of A looks like. We know what the set, the image set of A is. Okay, then we're supposed to prove that F is onto. So I can't just say, well, look at it. I can tell you that. We actually have to do something. So we look at it and say, well, I wrote it again. So let's look at onto again. And let's say, suppose let's see, suppose X is in B. Okay, we're going to pick an arbitrary subset, an arbitrary element of B. Then N of B equals 2, or N of B equals 3. So, not N of B, N of X, sorry, N of X, because it's in B. So now we say, okay, suppose N of X equals 3. Then X is a subset of A with 3 elements not containing five. So F of X equals X. We found an element in A that maps onto, it's an element of A not containing 5. And so F is the identity on that, and we found it. So X is the image of an element in A. So then we say, now suppose n of X equals 2. Then let Y equal X union 5. Y, n of Y equals 3. Y is an element of A because it's a set with 3 elements from the set 1, 2, 3, 4, 5. And f of Y equals X. So we found an element of A, a set with 3 elements in it that maps onto Y. Thus, F is onto. Okay, so the second question here is F 1-to-1? Well, for that, we go back here and say, how many elements are in F of A? Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n of F of A equals 10. N of A equals 10. Could F not be 1-to-1? Every element in A maps onto something in B, and it maps onto all of B, and they have the same number of elements. So F is 1-to-1 also. Okay, good. Prove that Z and N have the same cardinality. Isaac, yes, what's your question?
So I'm assuming that works both ways and that we can either prove 1-to-1 or onto, and then we get the other one if the sets have the same number of elements.
Well, we proved onto, yeah, I would say so.
Okay. So if we were proving that there was an inverse, not necessarily finding it, could we say that, like, if the codomain and domain have the same number of elements, do we only have to prove either onto or 1-to-1?
They have the same number. Yeah, that sounds pretty good.
Okay.
And in fact, I would make that as a proposition and have you prove it as a homework problem. You didn't expect that, did you?
Sorry, will you repeat that? My speakers cut
be
out.
able to prove that. Prove, let's say this, prove A and B are sets. The number of elements in A equals the finite sets equals the number of elements in B. Prove that if f, a function f from A to B is 1-to-1, it is onto, or f from A to B is onto, it is 1-to-1. I think that's a great problem. I gotta go home and think about it. Okay? Good.
Yeah, thank you.
I think we're out of time. So we'll save these practice problems for the next time. And we'll review and go over the new material in section 4.4 on Tuesday. Okay? So as I tell you, I repeatedly tell you, I try and put the lecture class notes out before class so you can take notes on it. I put them out every time, and at the end of the week's modules, there's always one that says class lectures or something like that. And I distinguish that from pre-recorded lectures, which are up with the pre-recorded lecture information. So this is always at the bottom of the week, and I put both days in the same, you click on the same page, and then that tells you where the slides are. Okay? Let me remind you of that every time. And so this week is whatever, what week are we in? 8? We're over halfway through the semester. Good. Okay, we're done for today. I hope you had a nice mini break and slept and caught up and recovered and are ready to roar. Okay, well, I'll see you Tuesday.
Thanks.
Good discussion.
Thank you.
Bye-bye.